Okay. Hello. Good evening, all.
Good
To,
evening, ma'am.
yeah. Today we'll be starting week 11, right?
Yes, ma'am.
Okay. So before we start, I would like to know how many of you have started week 11. Disha, you have started week 11.
Yes, ma'am.
Okay. You watched all the lectures.
Ma'am, not all three lecture I watch.
Okay. What about others? Have they started?
No, ma'am.
No. Okay. All right. So what I will do is, since none of you have watched anything, most of you, so maybe I can go with the slides and you can let me know where are you facing the issues.
Ma'am,
And
can you summarize week 11?
but you have not even watched, right? What will I summarize? I will go to all the slides. I will tell you what all is there. Um.
Okay.
Okay. Just can you see this? Can you see the screen?
Yes, ma'am.
Yeah. Before we go there,
Ma'am, you're not audible.
yeah, I'm not saying anything. I'm just hold on.
Okay, okay.
What is the deadline for your week 11 assignment submission?
Ma'am, 10 April.
10.
You have only 5 days left, so I would say please go to the lectures, solve the problems. So, okay, week 11, what we're going to look at is all the discrete random variables. Okay. All the discrete random variables. And when we say discrete random variables, what do we mean? We mean the random variables which take on discrete values. Okay. So we're going to talk about such kind of known distributions like quite popular these are. So the first one that we're going to look at is a Bernoulli distribution. The second one that we're going to look at is binomial distribution. And okay, like from we will also look at the what are the mean and variances. Same for binomial, we'll look at what are the mean and variances. Third is hypergeometric. And fourth one is Poisson distribution. Okay. So these are the 4 topics that we're going to look at. I'll go step by step. So first, let me go to the slides. And then if you have any further doubts, we can go over that topic in more details. Okay. So before we start with Bernoulli distribution, can someone tell me what do they understand by Bernoulli distribution? If you have watched the lectures, what did you understand Bernoulli distribution is? Anyone?
Bernoulli distribution is used when outcomes are to success or failure.
When outcomes are true or?
There are only two outcomes
Okay, there are only two
of
outcomes.
0 and 1, and for success and failure.
Yeah, right. So whenever you have just two outcomes for any kind of random experiment, we call such kind of experiment as a Bernoulli experiment, right? Bernoulli trial or experiment. So, like you can define many such scenarios, right? So we're talking about Bernoulli. Okay. So any random variable, or maybe we can talk about random variable first. So any random variable which takes on only two values, either a success or a failure. Okay. So there are many kind of such experiments where will you like the way experiment is defined when you will have either a success or a failure, right? So for example, you toss a coin and this is my experiment, okay? This is my experiment. And I define an event which says getting ahead, right? So when you toss a coin, you will either get a head or you will get a tail, right? So whenever you get a head, you toss a coin, you get a head, you call that as success. And you call tail as a failure, right? So it's not just when we are tossing one of your coin, we can define events like this. Even let's say I toss two coins. Now let's say in the second experiment, I toss 2 coins. And I can be interested in event of getting 2 tails, right? I can be interested in getting 2 tails. So in this case, like when you toss 2 coins, what all the possible outcomes are? You have HH, you have HT, you have TH, and you have TT, right?
Okay, ma'am. So we can decide an event on our own.
Yeah, you can decide, but depending on the questions that is being asked to you, on that basis,
Okay, so it would
you
be given
find
in the
out.
question.
Yeah, it will be given in the question. Now, okay, now let's say I define the event getting two tails. So what is your success and what is your failure? Can you tell me?
Yeah. Success would be TT, and all the rest three would be failure.
Right? So you have HH, EH, HT, they are failures. So it's very simple. Like it's just two outcomes, success or failure. That's all. So let's look at it carefully. Yeah. So we define what a Bernoulli trial is. Now, so what is a Bernoulli trial? Any trial or experiment whose outcome you can describe, you can classify as either a success or a failure. This is what we saw in the coin toss example. So in our experiment, when I am able to classify, like even in case of one random variable, we had, I mean, even in case of one coin tossing, uh, we, we, we were able to classify the outcomes of my sample space as either a success or a failure, right? Even in case of when we toss the coin two times, even there we were able to classify the outcomes as either a success or failure. So it depends on how you ask the event. I mean, what is your interest in? Like, how do you define your success or failure? So such kind of random variable, we call it as Bernoulli random variable. So few examples over here. Think
Ma'am,
hmm,
how to derive expectation for Bernoulli experiment?
how to define. Yeah, I will come over there. So first, look at some examples, right? So the first one we already saw. Second one, the experiment is rolling a dice, and success is we are saying getting a 6. So failure would be getting any other number, right?
Yeah.
Now, if the experiment is opinion polls of yes and no, and if I'm defining my success as yes, so failure should be no. Salesperson selling an object, so sample spaces sale, no sale. If I'm defining success as sale, my failure would be no sale. Effectiveness of a drug, non-effectiveness of a drug. If I'm calling my success as effective, we will call the failure as non-effective, right? So this is how you can just classify. Now, yeah, it is also important to look at the cases, the trials or the experiment whose outcome we cannot classify it as success or failure, right? So here, one example that is given to you is randomly choosing a person and asking their age, right? So if I'm performing this experiment, let's say I go to all of you and I select one person and ask your age. Okay. So does this come under Bernoulli trial? No. Why is that? Because it's not that I am explicitly saying that, okay, I'm asking, are you below this age or are you above this age? If situation like that we had, then we could have called such kind of experiment as Bernoulli. But here we're just going and asking their age. So let's say some person says, okay, I'm 19 years old. Someone says 23 years old. Someone says 20 years old. So everyone may be different, some similar or some same. But it is not just two outcomes. You cannot classify your outcomes on two groups, right? But in case your experiment was like you're going to randomly choose a person and ask whether you are uh, above 18 years or not? This will come under a Bernoulli's trial, right? Because you go to a person, let's say someone says 19. So you will mark that person as success, right? So you ask some other person and the person says 17 years old. So the person is not above 18 years old, so it is a failure, right? So it is important to understand like what situations, like how you have, what is your experiment basically, that is important to understand.
Okay.
Yeah. So that was our Bernoulli random variable. Now, when we talk about like when you studied in week 10, finding out the PMF for a random variable, right? So, I mean, any random variable you have, let's say any discrete random variable you have, X a discrete random variable, you will have some PMF associated with it, right? Probability mass function. So let's say if my X is taking the value 0, 1, 2, 3. So there will be some P of X, right? Some probabilities associated with each of these values, and all of these probabilities will always lie between 0 to 1, right? Because it's a probability. So it should always lie between 0 to 1. And if I sum over all these probability, Px over all X, it should add up to 1, right? So I can give some, let's say everything as 1 by 4, 1 by 4, 1 by 4, 1 by 4. So all of this add up to 1 also, and everything is greater than 0 and less than 1, right? All lies between 0 to 1. So this is a valid PMF, right? Now here, if we say that my X is a Bernoulli random variable, then this should also have some probabilities associated with, like some PMF associated with this random variable, right? So how do we define that? This is what we should know. Now, this Bernoulli random variable will have some parameter with it. So we call it as P, Bernoulli P, bracket we write P. And what is this P? P is probability of success, right? So, for example, like in our coin toss example, when we were tossing of a coin 2 times, we had HH, HT, TH, and TT as our sample space. And we defined the success as getting 2 tails. So what is, can someone tell me what is probability of success?
One by 4.
1 by 4. So if probability of success is 1 by 4, what can I call my probability of failure as?
3 by 4.
3 by 4. This is nothing but 1 minus probability of success. Because in case of Bernoulli random variable, you have only 2 outcomes, right? Bernoulli has only 2 outcomes, success and failure. And if the probability of success is 1 by 4, probability of failure will be just 1 minus probability of success. So in this case, 1 minus 1 by 4, right? This is okay. Now, so what do you call probability of failure as? You can write it as just 1 minus P, right? Now, how do we go about writing its PMF? So, if X is a Bernoulli random variable with parameter P, probability that your random variable X takes some value K is going to be P to the power X, sorry, P to the power K, 1 minus P to the power 1 minus K. Okay. This is the PMF for a Bernoulli random variable. So, and how, where does K belong? What is the range? What is the set of values that K can take?
0 and 1.
0 and 1. Why is that? Because X is a Bernoulli random variable, and the Bernoulli random variable has only two outcomes, which is success and failure. So, like in general, how we denote a success is we denote the success as 1 and failure as 0. Okay. So, this is how we write the PMF for a Bernoulli random variable. See how does it come? So you put, let's say you have to find probability. So if it is not there, let's say I don't know what my PMF is. Okay, if I am just writing X follows Bernoulli P. Okay, so what is probability X equal 1?
P
P. And what is probability X equals 0?
1 minus P.
1 minus P.
1 minus P. Now, just compare these two. If I put K equals 0, it means if I'm interested in finding the probability of failure, what will you get? You will get P to the power 0, 1 minus P. So P to the power 0 is just 1 and 1 minus P remains. So from here I get probability X equals 0 equal 1 minus P. And what happens? And what happens if you do substitute X equal 1? You get just P. So both are similar, you can see, right? So
Yeah.
this is what a PMF of Bernoulli random variable is. Okay. Now we looked at what Bernoulli trial is, what a Bernoulli random variable is. We looked at how you define its PMF. Now what is left is how do we find out its mean and variance, right? So someone had asked, I guess. So let's see if there is. Okay, I can do it over here. Or okay, so see what we saw. We saw X to be Bernoulli P, and probability that X takes the value K is P to the power K 1 minus P to the power 1 minus K for K belonging to 0, 1. Now, you know what is expected value of X. So, expected value of X. To find the expected value of X, what do? You sum over X time probability of X over all X, right? So, in this case, my X is taking the value 0 and 1. So, this would be 0 time probability of 0 plus 1 times probability of 1. Right? And what is this be? This is just 1. So expectation of a Bernoulli random variable is just P. Okay. Now coming to variance of X. What is variance of X? It is expected value of X minus expected value of X whole square. Right?
Yes,
Now,
ma'am.
what is so this would be sum over X minus mu whole square Okay. So, okay. What is your expected value of x?
P.
P. X minus P whole square. Okay. And this is what? This is just going to be x minus P whole square times P of x, right? Overall x. Now, your x is taking the value 0 and 1. So, if x takes the value 0, it is going to be 0 minus P whole square, P of 0, plus 1 minus P whole square, P of 1, right? So, this is just P square. P of 0 is what? P of 0 is 1 minus P. Plus 1, what is P of 1? P of 1 is P. So, 1 minus P whole square. P of 1 is P. So, I can take it common. I can take P 1 minus P common. And I will get P plus 1 minus P, right? Fine. This gets cancelled out and I am left with only P times 1 minus P. So, this is my variance. This is fine. This is fine. You got how we,
Yes, ma'am.
okay, fine.
Ma'am, how you cancel P and 1 minus P?
I didn't cancel P and 1 minus P. I cancel P and minus P. So this is what? This is P plus 1 minus P. So I cancel P minus P. I'm left with only 1. So if I multiply P times 1 minus P with 1, I get only P times 1 minus P.
Okay, ma'am.
Yeah?
Yes, ma'am.
Okay. So we saw what is the Bernoulli random variable? We saw its expectation, mean, and the distribution. So I think this is where this chapter ends. Yeah, tell me.
And how do we get u of x is equal to n into p?
How do we get?
Expectation of x is equal to n into p.
Where did we get expectation of x equal n times p? It is p, no?
What's the
I am talking about Bernoulli random variable. I didn't go to binomial random variable. You're getting confused with binomial and Bernoulli, I guess.
so n into p is for binomial,
Hmm.
but
I didn't.
sometimes we use that formula in week 10.
We use that formula in week 10 for solving some problems. Yes. But that is for binomial, not Bernoulli. So in case of binomial random variable, Bernoulli random variable, you have only two outcomes, 0 and 1, where probability of 0 is 1 minus p, probability of 1 is p, expected value of the random variable is p, and variance of x is p times 1 minus p. Okay, we saw the proof for everything. Now, not important, but okay, I'll just look at it. So, what did we see the variance as? We saw the variance of x as p times 1 minus p, right? Now, when and p is what? P is the probability of success, which will always lie between 0 and 1. So, what we say is the largest variance occurs when p equal half. So, when p equal half, you have variance maximum in case of Bernoulli. Proof not required here. So just one remark or observations that I could say. Okay. So that was all about Bernoulli distribution. Any doubt, anyone in Bernoulli distribution?
Ma'am, could you please explain second point?
Second point.
Yes, ma'am.
Or the second point. In other words, the most uncertain Bernoulli trials, those with the largest variance, resembles tosses of a fair coin. Yeah, I mean, see what we are saying. We are saying for a Bernoulli distribution, the largest variance occurs when p equal half. Okay. So the most uncertain Bernoulli trial, I mean, what we're calling the most uncertain Bernoulli trial is the trials, those Bernoulli trials which has the largest variance. So it means for which p equal half. So you remember like tossing a fair coin, probability of success is half. So what we're just saying is this resembles more like tossing a fair coin, right? Because probability of success is half. So variance will be maximum. That's all.
Okay, ma'am.
Okay. So the very fundamental, most basic discrete distribution that you are going to look at is Bernoulli distribution. It's very simple. You only had to take care of whether your experiment has two outcomes, success or failure, and how do you define your probability mass function? What is its expectation? What is the variance? That's all. Now, just a continuation to the Bernoulli trial. What we are going to look at is binomial random variable. Okay. So, yeah, just so okay. What we said is like if you have a Bernoulli random variable with two outcomes, we have this was a when two outcomes was success failure, we had Bernoulli P. But now let's suppose that you you have now, let's say, n IID. So when we say IID is nothing but independent and identically distributed. So imagine that like the same coin toss experiment. What we can do is, so like before we are just tossing one coin, right? And we said we had the two outcomes, success and failure, which is head and tail. Now imagine repeating the same experiment n times. So now instead of tossing a coin one time, you toss a coin, tossing a coin n times. Okay. And this, not just tossing the coin, you should toss it independently. I mean, each of the tosses are independent of each of the tosses, and they all should follow the same distribution. I mean, when I'm tossing a coin, one time I know that it follows the Bernoulli P. If I toss a coin, let's say two times, I know it is going to follow again Bernoulli P, right? The third coin that if I'm going to toss the coin third time, again it will follow the Bernoulli P, right? So every time you repeat this experiment of tossing a coin, and you do this experiment repeatedly and independent of each other tosses. So every time you have the same distribution coming in, right? So what happens is, like when you add all such, if you take a sum of all these n IID trials, this is what we call it as binomial distribution. Binomial distribution. So what is the binomial distribution models? Binomial distribution models total number of successes, total number of successes in n IID trials. Okay. So if let's say in the coin toss experiment, a single coin toss experiment, if I am defining my success as getting ahead, and if I am repeating this experiment independently n times, then at the end, what I get after summing, after taking all these tosses into consideration, what we get it as the total number of successes that you get. So just for notation, that what I'm going to do is I can call x1 as outcomes on the first toss. Okay. So what will x1 take? Either head or tail.
Yes, ma'am.
So head or tail, I can say it as success or failure. Again, I can talk about x2. And I can say x2 is outcome on the second toss. Again, what it will take? It will take a head or a tail. It means success or a failure. You go on like that and you repeat this n times. Okay. So now if I add all of this, so if I add x1 plus x2 plus up to xn, this will give me now a binomial distribution, the parameter n comma p. So if we notice that in case of Bernoulli, we just had the parameter n because we had only one trial. But now in binomial, you are repeating the Bernoulli trials n independent times, right? So even the number of times you are repeating the experiment, that also comes here. So that in the parameter, and that is n. N is nothing but number of times you have repeated the experiment. So if you add all of it, if you add, see, x1 will take 1 comma 0, x2 will take 1 comma 0, right? And so on till xn is taking 1 comma 0. So if I add all of it, what it should give me? It should give me total number of successes in trial, right? Do you agree to this?
Yes,
What
ma'am.
are actual extras of extent probabilities?
X1,
The
no, they are just random variables. So each exercise, exercise are Bernoulli P. Right? So if I add all of them, it should give me total number of successes in n trials, n independent trials. Do you agree to this statement?
Ma'am, Bernoulli P means probability of success.
Yes. Not probability of success. When I'm saying xi is Bernoulli P, it means I am saying that my random variable xi follows a Bernoulli random variable with the probability of success P,
Okay.
right? Now, if and I know that my xi is Bernoulli P, it means it can take only two outcomes. It can either take 1 or it can take 0. Okay. Now, if I repeat this, I mean, if I repeat this experiment n independent times, okay, if I repeat this experiment n times independently, then what happens that if I repeat this and take the sum of all of it. So x1 can either be 0 or 1. Again, x2 can either be 0 or 1. x3 can either be 0 or 1. xn can either be 0 or 1. Okay. So maybe for simplicity, what I can say is, assume that let x1 takes the value 0. It means what we are saying is, in the first coin toss, I got a tail. Okay. First toss, um, the first toss I got tail, right? Let's say x2 also takes the value 0. It means second toss I got tail. Let's say x3 is 1. It means third toss I'm getting a head, right? So suppose I did, instead of n times, I performed the experiment 3 times. So I tossed the coin 3 times independently, right? And notice that each of these xis are Bernoulli P, right? Each of these xis is Bernoulli. In this case, it is half. Now, if I add x1 plus x2 plus x3, what will you get? What will you get if you add x1 plus x2 plus x3? X1 is 0, x2 is 0, x3 is 1. What is x1 plus x2 plus x3?
1, ma'am.
1. So what did this 1 give you? This is coming out as 1, means in these 3 trials, 3 coin tosses, you got 1 success. You got 1 head, right? Now if I would have done x4, I mean, if I would have tossed the coin 4 times and I would have gotten again x4 as 1. So fourth toss, if I get a head, and if I add x4 over here, so I will get here 2. So it means in 4 tosses, I got 2 successes, right? Right?
Yes, ma'am.
So that is what we have written over here. So in general, if we toss, if we repeat the Bernoulli trials n independent times, I mean, and all these trials are identically distributed. I mean, if x when we say, you would have to understand what is mean by identically distributed. So independent, I mean, all these x1, x2, x3 up to xn all should be independent. Okay. What is mean by identically distributed is, in IID, is like if x1 follows a Bernoulli P, x2 should also follow Bernoulli P. x3 should also follow Bernoulli P. So on till xn should also follow Bernoulli P. Okay. This parameter P should not change for any of these random variable. So like in our coin toss example, for every experiment, for every trial, you could see that my P is fixed. I always have this Bernoulli half, right? So that you should take care. So what we are saying is my binomial random variable models the total number of successes in n IID trials. Okay. This is clear?
Yes, ma'am. Ma'am, can you give example on?
Example I gave, no, the coin toss experiment.
Yes, ma'am.
Do you mean any other example?
Yes, ma'am.
Okay, we can take maybe a die example. So, okay, suppose my the first trial or maybe the experiment I'm going to take is um, throwing throwing a fair die. Rolling or not throwing, rolling a fair die. Okay. So what I can define my success as? Success is, let's say, getting ahead, getting a 6. Getting a 6. Okay. So what will the failure be? Not getting a 6?
Yes, ma'am.
So if I have to say, so again, this is again a Bernoulli random variable, right? Because it has two outcomes, success and failure,
Yes,
right?
ma'am.
So I need to write Bernoulli P, right? So P is what? Probability of success. P is probability of success.
Yes, ma'am.
What is P here?
1/6.
1/6. Now let's say I repeat this experiment. So I will roll. Now rolling a fair die, what I will say is roll the die, let's say 5 times. Okay. So every time you roll, either you get a 6. So let's say x1, what I will write is, so x1 is what? Outcome on the first row. Similarly, x5 will be outcome on the 5th row. And we are saying all these x1, x2, x3, x4, x5, all of them follows Bernoulli P. Okay. So in this case, Bernoulli 1/6. Okay. So each of x1, x2, x3, x4, x5 will either take 0, 1, right? Will either take 0 or 1, right? This is fine.
Yes, ma'am.
Now, if I add everything, so suppose I get x1 to be 1, x2 to be 0. This is just one example, okay? I mean, it not become exactly this. It can be anything else. X3 to be 0, x4 to be 1, and x5 to be 1. Now I add everything. I add x1 plus x2 plus x3 plus x4 plus x5. What will I get? I get 3.
Yes, ma'am.
So what does this mean? It means in 5 of these independent roll of the die, I got 3 successes. 3 successes means on 3 rolls, I got the outcome as 6. right? This is what it means.
Yes, ma'am.
That's all. That's all is, so this sum, right? This, if I have to write this, so what I can call all these x1, x2, x3, x4, x5 addition as, let's say, y. So my this y, which will follow a binomial random variable with the parameter 5, comma 1 by 6. Okay.
Yes, ma'am.
Yeah. That's all. I think you will come across many examples. So do not worry about it. You will see many examples and will work out how to define all these problems. Okay. So, okay. We were talking about independent and non-independent, independent wells. So one example over here. So the example says, consider the experiment with 3 balls are chosen without replacement from a bag containing 20 red balls. So let's say you have a bag. You have a bag which has 20 red balls and 40 black balls. Okay. The number of red balls drawn is recorded. So let's say I define my random variable x as number of red balls. Okay. So what we have to ask is this a binomial experiment? So this is the question. So what we're doing is, you have to choose 3 balls, okay? 3 balls you have to remove without replacement. So what does it mean is, like, you pick one ball, you note down its color, and you don't put it back into the box, and then you remove another ball, you note down its color, again you remove one ball, you note down its color, and this way you remove 3 balls, right? So let's say ball 1, ball 2, ball 3, right? So can someone tell me if this is a binomial experiment or not?
Yes, ma'am.
Yes?
Yeah.
Anybody agrees?
Ma'am, how this is a binomial experiment?
What do you think? Is this a binomial experiment? Okay. Whoever mentioned whether this is a that this is a binomial experiment, can you tell me why this is a binomial experiment?
Ma'am, in our sample space, we have only 2 outcomes, red or black,
Okay.
and
Hmm.
you have to draw a red ball and we record it. So,
Not red ball. We
let
have to
us
record
say
3 ball. We have to record 3. We have to take out 3 balls.
three
Tell
balls.
me. Yeah, tell me. Consider the experiment where 3 balls are
So,
chosen.
probability of getting one red ball will be the success, and if not, it will be a black ball, which is a failure. So, I
Okay.
think it is a Bernoulli experiment, and the collection of these trials for 3 red balls will be uh, binomial experiment.
Okay. Okay. I mean, okay, this is fine that you are calling getting so how you have defined is you're calling a red ball getting a red ball as success. This is fine. So getting a black ball is my failure. Fine. Okay. Now, you have to draw 3 balls. So let's say my x1, I will note down. So x1 is on the first trial. Which ball did I record? So let's say x1 is the ball you recorded on the first trial, right? x2 is the ball you recorded in the second trial. x3 is the ball you recorded in the third trial. Yes, they are, that you are drawing 3 balls, but look at this carefully. Like it says you are drawing 3 balls without replacement, right? So what happens when you draw without replacement? So like if I'm saying that probability of success is getting a red ball, so probability of basically probability of 1, which is success I'm denoting as 1. So probability of 1 is what it will be, 20 by 60, which is 1 by 3.
Yes, ma'am.
Now if I have to, so I pick one ball, I note down, let's say it is red, whatever it is, and my success defined as getting a red ball. I am not picking this ball back because this is without replacement, right? So now the number of ball that is left in the bag is 59. So in the second trial, when I want to pick a ball, so in that case, my probability of success becomes 20 by 59, right? And it is not equal to 1 by 3. Again, in the third trial, when we pick one ball, note down when we pick one ball. So now in this bag, we have 58 balls left because we did not bring back the ball in the bag. So again, probability of success changes, right? So this is not a binomial experiment. Why? Because we here I had talked to you about like why you should take care of IID. I mean, all of these random variables should follow the same distribution, right? I mean, my probability of success cannot change in every trial. So here what is happening is in every trial, even though like if I'm defining it as getting a red ball as success, but in every trial, my probability of success is changing. So if my X follows a Bernoulli 1 by 3, which is from here, this doesn't remain 1 by 3 in the second trial and in the third trial. So that fails. And that is why it is not a binomial experiment. Okay. So the catch is here without replacement and with replacement. So in binomial experiment, you should always have with replacement. Okay. Just take care of that.
Okay, ma'am. Ma'am, here our experiment is a number of red ball. So, without replacement case, and number of red ball is also reduced or not?
Yeah, I mean that will depend, you know. I mean you don't know like here. See here, everything you're talking about is uncertainty, like probabilities, right? So I can't tell it for sure that in my first trial I got a red ball or a black ball. If I got a black ball, my number of red ball in the bag is going to be same in the second trial. But in case I got the red ball in the first trial, then my number of red ball in the bag is going to change, right?
Yes, ma'am.
Okay, so no, this is not a binomial experiment, right? Why? Because the balls are chosen without replacement. The color of the first ball will affect the chances of color on the next ball. Independence criteria is not satisfied. Okay. We talked about IID. Now we are going to, so we understood what kind of setting a binomial random variable will have. Now we'll look into like what is the probability distribution for a binomial random variable. Okay. So here, see, the setup is like, suppose that n independent trials are performed, each of which results in either a success with probability p or a failure with probability 1 minus p. Okay. And let x denotes the total number of successes that occur in n trial. Then x is said to be a binomial random variable with parameters n and p. This is exactly what we discussed. And how do we write a binomial random variable? We just write, so this is the notation. So x follows a binomial with two parameters n comma p. Okay, where p is probability of success in one trial and n is total number of trials. Okay. Again, another question over here. The question is, consider the experiment of rolling a dice until a 6 appears. Is this a binomial experiment? Is it a binomial experiment? Anyone?
I think, ma'am, no.
Oh, okay. Why is that?
Because the probabilities are not independent.
The probabilities are not independent? What do you mean by probability is not independent?
Like in each trial, when we toss the dice, that depends on the outcomes.
Okay.
Uh,
Yes, you're
that
right that it is not a binomial experiment. Why is that? Because see here, the experiment says rolling a die. So what is first of all, the first thing that you should do is write what is your experiment. So experiment is rolling a die. Fine. Now, thing is, you are rolling a die until a 6 appears. Okay. So that. I'm interested in getting a 6, right? So what is my success? Getting a 6?
Yes, ma'am.
Failure is not getting a 6. Okay. So we are saying we roll a die until 6 appears. So it is quite possible that your 6 can occur on the first try. Okay. Or you don't have, I will just use not 6 as this. Or you get a 6 on the second trial. Okay. Or it is possible that you get the 6 on the third trial. Right? You keep on rolling the die because until you get a 6, you are going to roll the die. So what you get is either your 6 if I call my random variable x as getting a 6, right? So it can either come on the first trial, or on the second trial, or on the third trial, or on the fourth trial, or on the fifth trial, and it will keep on going. It will keep on going until the 6 comes, right? So every time what happens is like these okay. Okay, so getting a 6, so every time probability of success differs, right?
Ma'am, that's because we are considering the conditional probability that one has means not 6 has already occurred, then what's the probability of getting 6? Are we saying in that way?
No, we're not saying in that sense. Um, See, for the experiment is you roll the die until 6 appears, right?
Yeah.
So until 6 appears, it means it can just keep on going. It will not stop. I mean, it can go to infinity, to
Yeah.
say.
Minute.
So there is no fixed trial. There is no fixed trial on which you can say like how to say that? Okay, like
We don't
either
know how much number of time we have to repeat the same experiment.
yes, and every time this probability of getting a 6 changes. This time it's 1/6, right? In this case, it is going to be 5/6 times 1/6. In this case, it is going to be 5/6 square times 1/6. Right? So every time it keeps on changing, and that's why this is not a binomial experiment. Yeah. So it has a very special name also, such kind of experiment. It is called a geometric distribution. I don't know if you have studied this, but this is a very special name. It's called geometric distribution. Such kind of whenever you come across situations like that, you model it using a geometric distribution. I think it's not in your course, but just since this example is there, I just gave it. Yeah, see. So number of trials, we don't know where does the experiment stop. This is fine, right? So this
Yes,
example, like in the first, I think when we were talking about this balls, like red and black balls, and we were saying we are going to choose 3 balls without replacement. There, it was not a binomial experiment because the probability of successes in each trial differs, right? But here, why we are not calling it as a binomial experiment? Because here we don't know where does the experiment stop. We don't know whether I'm going to get it as one trial or second trial, third trial, fourth trial, and so on. It will keep on going. So n is not fixed here, and that is why it becomes a it becomes a non-binomial experiment. Okay. Okay, I think we have already seen all of this. So I would suggest you to like go through the videos once so that you understand how all this thing is coming. So maybe okay, let's just see this one maybe. Okay. So we are talking about 3 independent Bernoulli trials. We are talking about here 3 independent Bernoulli trials. P we are saying is the probability of success. So if we have 3 independent Bernoulli trials, let's say on my first trial, I get success. On my second trial, I got success. And on my third trial, I got success. Here we are saying first trial success, second trial success, third trial failure, success, failure, success, and so on. Okay. So since all of these trials are independent, that we have said, independent Bernoulli trials. So probabilities we can just multiply. So probability of success is P. So P times P times P. Right? Then if it is a success, failure, it means P times 1 minus P. If it is SFS, it is P times 1 minus P times P. Right? This is how you can find out the probabilities. So if I define, you have n equals 3, right? So if I'm calling it as X follows binomial with 3 trials and probability of success as P. Okay. So if you have so if the random variable X follows a binomial distribution with parameters 3 and P, so it means we are performing the experiment 3 times. And what does this random variable give me? This random variable should model the number of successes that you are going to get in 3 trials. Okay. So what all the values you think my X should take? I'm interested in number of
0 to
successes.
3.
0
0
to
to
3.
yeah.
So you'll get 0, 1, 2, 3, right? So you have 4, these values. So you'll have to find what is the probability that X takes the value 0. What is the probability that X equal 1? What is the probability that X equal 2? And what is the probability that X equal 3? Right? All this you need to find. This is my PMF for binomial distribution, right? So if you look over here to this table, probability of X equals 0 means what? It means you have 0 successes, correct? It means you have all failures. 0 success means all failure.
Yes,
So
ma'am.
that would be just
8th case, 1 case.
8 case 1. So probability of F. It means in all the three trials, like in X1 you got 0, in X2 you got 0, and in X3 you got 0. Right? This is what we mean by X equals 0. Means in all the 3 trials you got failure. Probability of F. So what is that? It is just 1 minus P whole cube. Right? Now if I talk about probability X equal 1, it means you got 1 successes in the 3 trials. On the first trial, the second trial, third trial, all the 3 trials combined, you got only 1 successes. So you can see that in the 7th case, in the 6th case, in the 4th case, you have 1 successes, right? So to find probability X equal 1, you can add this probability plus this probability plus this probability. Okay. And that will give you probability X equal 1. So, the thing is, you cannot always go and do this table. Like every time this number of times you are performing this experiment is not going to be this small. what happens if some experiment has been performed some 10 times or 100 times? You cannot go and calculate the probabilities like this, right? So there is a formula that has been given for this Bernoulli random variable. Like how do you find the PMF probabilities if you have a random variable that follows a binomial distribution? So it is so let's say my x is binomial with number of trials p and number of probability of success p. So probability, so and I know that, okay, so probability that x takes the value k is n choose k, p to the power k, and 1 minus p to the power n minus k, where k will take the values from 0, 1, 2, so on till n, right? Where k is number of successes that your random variable will take. Okay. So this is how you can find the probabilities for each of the values your random variable takes. Very simple. And this is, I mean, I think you can easily derive it, just from a combination, no? So see, when you are saying probability x equal k, it means out of n trials, let's say out of n trials, you got k successes, right? But you don't know which trial you got the successes. So first you will have to choose those k trials. So how can we do that? We can do n choose k, right? So first we choose those k trials, and on those k trials we have the success, and all these trials are independent. So I have a probability of success which is p, and you got the success k times, so p to the power k, and times failure, right? So if in n trials you got k success, so n minus k will be failure, n minus k trials, and probability of failure is 1 minus p. So probability of failure to the power n minus k. That's all. Is this clear? How did we get this formula?
Yes, ma'am.
Okay. Okay, what else is there? So see, this is exactly what we are talking about, that you will have to add all these probabilities and you get this distribution, right? Maybe when you watch the lecture, you can go over it once. I think that is all in this lecture. Any doubt? Any doubt from binomial?
No, ma'am.
Oh, okay. Let's move to the next one. Yeah, so here we are just talking about the definition. So what is the binomial random variable? It is like you call any random variable a binomial random variable with parameters n comma p. So that represent the number of successes in an independent. This is very important. I mean, if all these trials should be independent trials, right? And each trial is a success with probability p. Okay, so all this we have already seen, so it's not. Do it again. We can do this example. Very simple coin toss example. So what we are saying is that we have a coin and we are tossing it 3 times. So my x follows again a binomial random variable with the parameter 3 comma. Since you're tossing a coin 3 times, that's why it is 3. And probability of success is half because we are calling success as head and failure as tails. So what does this mean by this random variable x? It counts the number of heads in the tosses, right? So, and I know that probability x equal k is n choose k e to the power k 1 minus e to the power n minus k, right? So what is probability x equal, since x will take here value 0, 1, 2, 3. So what is probability x equal 0? What is it? What is x probability x equal 0? N choose 0, which is 3 choose 0. P to the power 0, which is 1 by 2 to the power 0. 1 minus p to the power n minus k. So 1 minus 2 to the power n is what? 3 minus 0, right? So 3 choose 0 is 1, 1 by 2 to the power 0 is 1, 1 by 2 to the power 3. Okay. Similarly, can you tell me what is probability x equal 1?
3 C1 1 by 2 power 1 1 by 2 3 minus 1.
Simple, right? You should just remember what is this EMF of a binomial, and you should be able to find all the probabilities. Okay.
Yes, ma'am.
Okay. Okay, I think here we're going to just talk about the graph. Um, I'll skip this part. You can look over it. Skip this.
Ma'am, by seeing questions, how we can tell about that it's left skewed, right skewed, and symmetric?
You want me to do this also? Okay. You mean, okay, repeat.
Ma'am, ma'am, like some question was given for finding right skewed, left skewed, and symmetric. How we can say that it's how we can done that?
How to say that it is right skewed, left skewed, or symmetric?
Yes, ma'am.
So, see. So this graph appears, I mean, about where this is centered. I mean, it looks very similar both sides, right? The shape is similar, right?
Yes, ma'am.
So this is symmetric, okay? When we talk about right skewed, it will be more like this skewed on the right. When you have something like this, we call this left skewed. So you see, it's skewed on the left side.
Okay, ma'am.
Yeah. So for binomial, like in case that your I mean, if your number of trials is quite large, when n is quite large, your binomial random variable will always appear to be symmetric. Okay. And when you have small n, then you have issues. I mean, not issues, I mean, then you have different cases. If n is small, but p is 0.5, probability of success is 0.5, then in that case, it is symmetric. If p is large, you will have a left skewed graph. If p is small, you will have right skewed graph. So depending on what the size of n is and what your p is, you can tell from there.
Okay, ma'am.
Okay. We will do till lecture 10.5 and then remaining we can do in the next session. We only have half an hour left.
Okay, ma'am.
Yeah, okay. See, we looked at what binomial distribution is. Now let's try to look at some examples, like of how the binomial distribution kind of question comes. Okay. See, the question is, consider a company that sells goods in packs of 3. Okay. So let's say you have let's say you have all these packets, okay, and in every packet you have 3 items. Okay. So the production process of the goods is not very good and results in 10% of goods being defective. All right. The company believes that customers will not complain if 1 out of 3 in a pack is of bad quality. However, will complain if more than 2 out of 3 are of bad quality. Okay. So any pack I take, say I take a pack of goods, it has 3 items. So what the company believes is like if in this pack of 3, if 1 is bad, the customers will not complain. But if 2 turns out to be bad, then they're saying the customer will complain. The company wants to keep number of complaints low, say at 3%. How do we help the company analyze the situation? Okay. So it doesn't want, okay, let's see what do we want to analyze, right? So what did the random experiment looks like? We had a pack of items which has 3 goods in it, right? Now, the experiment is that you choose the good from here. You choose one, right? So when you're selecting one item from this pack of 3 items, you will have either that item to be good because what our setup was? Our setup was that the company which is selling this products items, they doesn't want more complaints. So let's look at it more carefully. So we will have either a good product or a bad product. So this is my sample. So what I can say is I can call success as good, I can call failure as bad. Okay. So we also said that in a pack of 3, probability of defective item was 10%. I mean, 10% of the product goods were defective. So probability of an item being defective is 0.1. So it means probability of success. What is the probability of success going to be?
0.9.
0.9, right? Because the success is the product being good. So the product being good means we want that is a success. So that should be 0.9. Now in okay. Now what do we want to know? So this is done. This is done. We want to know the number of good items in a pack of 3, right? So okay. We have total of 3 items. So n equal 3. And x is what? Number of good items in a pack of 3. Okay. So n is 3, p is 0.9. Now what happens? So what did we get our setup as? We had a pack of 3 items. We defined the success as getting a good item and failure as bad item. X was binomial with n to be 3 and p to be 0.9, and x will take the values 0, 1, 2, 3. Okay. So you got you can find all these probabilities now, right? This is fine.
Yes,
So
ma'am.
now what we find the probability. Okay. So what we are saying, what the company wanted. The company wanted that the complaint should be not at least should be max 3% from the customers. It shouldn't go beyond 3%. Okay. So also the claim that the company made that if the number of products, number of goods or items in that pack, if 2 or more are of bad quality, then the customer will complain. Okay. So when will the customer not complain? When you get the number of bad items to be less than equal to 1. So, okay, we had defined X to be number of good items, right? I guess that is what we define and find probability. Yes, we define the number of good items, fine. So, we want the number of good items to be it's the same that we found, okay. Greater than or equal to 2. This is equivalent of saying that it is
Ma'am, probability of 2 and probability of 3.
I
We can add.
right. So this is what? This is probability that X equal to 2 plus probability that X equal to 3. So this is same as saying that 1 minus probability X is less than equal to 1, right? So that is why here it written probability X less than equal to 1. That's the only reason. So that's why I did that. But okay. So
No,
what?
but that changes based on how we like consider X. It's to be like okay or the defective one.
So the way we define random variable as uh, number of good items in a pack of 3. So what the question said is the customers will complain if they get more than 2, yeah, more than 2 or more than 2 in a pack of 3. Bad one if they get. So if they get more than 2 good one or 2 good one, then we are fine, right? So probability that X is less than equal to 1. So what we said is this is also equal to probability X less than equal to 1. And this we got to be 0.028, which is 2.8%.
Ma'am, in this
Why
case,
are
like if it's
yeah.
ma'am, in this case, the given question is that कि भाई हमारा 3% से कम हो या means error limit हो. So what we have to do is what we are doing is 1 minus probability of X less than equal to 1. So that value should be like greater than 97%.
Yeah. So we are finding it. We are finding the wrong thing. So yeah, the setup was that the complaint that they get shouldn't be more than 3%. Should be less than 3%. So they will get the complaint if the number of good items are less than equal to 1, right? They will get the complaint if the number of good items is less than equal to 1. This is fine, right?
If X is taken as the number of defective product, then yes.
No. I mean, what we are saying is X is still defined as number of good items in the pack. This is same, no difference. So now if number of good items is less than equal to 1, then the customers will complain. That's fine, no?
Ma'am, could you scroll a bit up like
Yeah.
ma'am, could you scroll to a previous like the
Yeah.
where this question was defined just a bit.
Yeah.
Mm. The complaint will not complain one of the three packs. Okay, or more. Okay, will not complain.
Hmm.
Okay. Okay, ma'am.
Okay.
Yeah.
So what so we wanted to set up this problem, right? So how we define everything is we are defining the random variable x to be number of good items in the pack. So the customer will complain if the number of good items is less than equal to 1. Right? That is what we have written here. It's fine. X denote number of good items. If number of good items is less than equal to 1, then the customers will complain. This is fine, no? And this probability we found out to be 0.028, which is 2.8%. Okay. So 2.8% is less than 3%, which was the goal set by the company, goal achieved. So however, the company set 2.5% as the threshold, then 2.8 would have been more than 2.5 and company would have not achieved its goal. Is this making sense? Is this clear? Is this problem setup clear?
Ma'am, last part, can you explain once again?
Okay.
Ma'am, the question said, the statement said, like if we want to keep the number of complaints low, that is less than 3%, and it's defining as like if two or three are of bad quality, then we will get a complaint. That is same as saying as when we are having 0 or 1 of good quality.
Two of
0 or 1 of good quality. That the reason why we are taking that?
yeah. 0 or
Oh,
1 of good quality, yeah.
okay, got it.
Um, okay. Yeah, so here, see, the company claim was that the customers will not complain if they find in one pack less than less than or equal to one item to be defective. Okay, so if sorry, more than one, if they find if the customers will not complain if they find less than one item to be defective or less than or equal to one item to be defective. So that probability we found, and we found it to be 0.028. And the claim that company made is like if it is less than 3%, they don't want more than 3% customers to complain, right? So they don't want more than 3% customers to claim. And according to all this, the setup, what we got is that 2.8% people will complain, okay, which is less than the company expectation, which they have set it to be 3%. So whatever the company wanted, they have achieved their goal by keeping this setup of like probability of defective and non-defective. Okay.
Okay, ma'am.
Okay, maybe this you can solve. The question is roll 4 fair dice. Define success as getting a 6. Find the probability that 6 appears at least once. So first of all, can you tell me what is N?
4, ma'am.
4. What is P?
Half. It's a fair dice. Fair dice, it's 1/6.
1 by 6.
Yeah.
So for the first question, it says find the probability that 6 appears at least once. It means you have to find probability X greater than equal to 1.
Yes, sir.
So this you can also write it as 1 minus probability that X is less than 1. This is much easier to solve because we just have to find the probability for X equals 0 and X equals 1 and we can be done. But if
Ma'am,
you find,
just X equal to 0 will do, na? It's less than 1.
sorry, X equals 0. Yeah.
Hmm.
In the second case, it is 6 appears exactly once. So you have to find probability that X equal 1. In the third case, 6 appears at least twice, so X greater than equal to 2. So these are the kind of setup problems you will get. Previous one was quite easy. Let's look at this. Here, the question says each ball bearing produced is independently defective with probability 0.05. If a sample of 5 is inspected, find the probability that none are defective or 2 or more are defective. So for the first of all, you need to define your random variable. So how will you define your X to be? How do you define your random variable to be?
Ma'am, X is like it's considering defective and non-defective. So that's going to be like non-defective with
0 and 1, ma'am.
No, I'm not asking about the values that it takes. I'm asking about how will you define your random variable? What will you call your random variable as? Like, what does it model?
the number of defective that we are having in like
Yeah. So I can say X to be number of defective ball bearing. Okay. So what is N in this case? 5, because 5
Yes, ma'am.
are inspected. What is P?
0.05.
0.05. That is probability of defective ball bearing. Okay. So if I'm saying in the first question, none are defective, it means what we have to find? Probability that X is
0.
0.
right. So that we can do. What happened in the second case? 2 or
2,
more are defective.
that is X is greater than equal to 2.
Yeah, that's all. So the only thing that you have to do is correctly identify what your random variable models, what your N is, what your P is. Then you will be done for the binomial questions. Mhm. Let's look at this question. It says a satellite system consists of 4 components and can function if at least 2 of them are working. Okay. If each component independently works with probability 0.8, what is the probability the system will function? Okay. So the first thing that you should look at, what probability do you have to find? So here you have to find the probability that system will function. Now the question is, what do you mean by system will function? System will function means out of 4 components, at least 2 components are working. So probability that at least 2 components work. Okay. So probability that at least 2 components work. So how should you define now? Now is the time when you should introduce your random variable. So what will you call your random variable x as? How will you
X is the
define it?
Number of components working.
Yes, number of components working. Okay. So that is x should be greater than equal to 2. And here n is 4. What is p? What is probability of success?
0.8.
0.8. Right. So now you can find it. This is probability x equal to plus probability x equal 3 plus probability x equal 4. Just find all these probabilities and you should get the answer. Okay. Okay, this is the last question. Yes. Yes. Can you solve this question? How will you proceed for this question?
Then probability of each question to be right is 1/4,
Okay.
and probability that each one will get 4 or more correct answer is then it will be x greater than 4. Is correct.
Hmm.
Ma'am, actual take values correct and incorrect.
Yes. 4 or more correct answers, right? So you have 5 questions. So either it can be correct or not correct.
Ma'am, it's like saying that all the 4 questions, first thing is all the 5 questions are independent. It's like saying that we are performing the answers to each one questions Yeah, and for each question's answer, it's an independent choice. If it's for
Yes.
so in that case, it's P of X greater than equal to 4.
Hmm.
In that way, also we see it.
Yeah, it is probability x greater than or equal to 4.
Mhm.
So n is 5, p is 1/4. That's all.
Hmm.
And that should give you the answer. Yeah. So that's exactly what you have to do. Okay, I don't think you need to know the proof for expectation and variance. I think we already did.
Yes, ma'am.
So you just have to find the expectation and variance. Just try it out. The way we did it for Bernoulli, it will be more like similar. Then it will much difference. Okay, yeah, we can go quickly. So see, we know each of these exercises are Bernoulli random variable. So I can write my binomial random variable as sum of these n Bernoulli random variable. So if I have to find its expectation, so expectation of x, so that will be expectation of x1 plus x2 up to xn. And since we have studied before that expectation follows the linearity property, so that will be nothing but expectation of x1 plus expectation of x2 plus up to expectation of xn. And each of these expectations are nothing but p. And these p's are summed n times. So it is nothing but np. So expectation of a binomial random variables turns out to be np. Now the same way, if you have to find the variance of x, so we replace x by x1 plus x2 up to xn. And since all these xi's are independent, we are able to write variance of x1 plus x2 plus up to xn as variance of x1 plus variance of x2 up to variance of xn, right? And we know that each of these x1, x2, xn follows Bernoulli P. And we know that their variances, the variance for Bernoulli random variable is p times 1 minus p. So we add it n times and we get np times 1 minus p. That's all. So it's quite easy. We have already looked at most of it. So what you need to remember is for a binomial random variable, your expectation is NP and the variance is N times P1 minus P. While in case of Bernoulli random variable, you had expectation as P and variance as P times 1 minus P. In binomial, you're multiplying N for both expectation and variance. That's all. That's all what is happening. Okay. All right. So we are already 10:06. So we have only been able to complete till binomial random variable. Maybe next class. I mean, you should also go ahead and watch the lectures. If required, we can do a revision of hypergeometric and Poisson in the next class. Okay. So today we'll close over here.
Okay, ma'am.
So do not skip the lectures. Please watch it and see wherever it is not clear, just go through the lectures once and try to solve the problem so that you get clarity on what is happening.
Ma'am?
Yeah.
Tomorrow is the last day for weekly extra activity 3 for reviewing, and I got only 2 reviews out of 3. What will
It's
be?
okay. I think all that is taken care of. Like, if you get less reviews, your summation, whatever you have submitted, will get checked by other people, and then you get the marks. So don't worry.
Oh, okay. Okay, thank you.
The only thing
Uh,
is you should complete your review.
Ma'am, I completed my weekly assignment, extra weekly assignment, but I just forgot to change the view option to IIT Madras. So two of the reviews gave me
Seven.
and get access.
Okay.
Yeah, but I completed my activity. So if I get a good like review in the third review,
Hmm.
then it considered as a full marks, or it will be considered as a like
No, it is considered as full marks. I mean, not full marks, like whatever is the average, whatever.
oh,
Yeah. Okay. All right. Okay, then we'll close for today, and whatever is left, we'll try to do it in the next session. But you also please watch the lectures.
We will be having an one more session for this week, like beside the regular that
No, no,
question.
no, no. You won't have.
ma'am, in end term exam, all 12 weeks will be come in the exam.
Yes, all 12 weeks.
And so, what will be the weightage of the?
It will be. You will be informed before the exam. Most of
Okay,
it would be mostly from week 9 to 12, but you will also get few portion from week 1 to 8.
so major will be 9 to 12, and
9
then
to 12.
it will be divided in the upper weeks
Yes. Yes.
above.
Okay.
Okay, ma'am.
All right. Let's close for now today.
Ma'am, I have a few
Yeah.
doubt. Like, I just shared your PDF in the chat. If you just please go through that. The last question that we discussed in the last class, na, I
Yeah.
tried to do it the same with using the probability and that probability both the approaches, but I'm not able to identify like what went wrong there in the first in that.
The cricket
Is it the
wala
name?
question. No, the cricket book cricket is something we were discussing. No.
Um, it was a question. Yes, ma'am. The cricket one.
Yeah. Did you find any other example?
Ma'am, another example I did not like. I tried the same question using the two different approach. One, what I thought that using the probability that should give better.
Independence, definitely not.
Yeah, independent it is not. So the probability I used the probability with varying that. Uh, yeah. Yeah. First approach use tried using the probability tree.
Hmm.
The first approach, but like there is only one branch that goes like when I'm not out. The complete only one branch. So if I'm saying that all are this not out, not out, not out, and all, so it should be like 4 by 5 raised to the power 5. But in the rest of any branches that I took, at least I get out in one of them.
You have not mentioned the solution here, right?
Uh,
I don't
hmm,
see the solution for this question.
it's written in the pan black and blue that I have like. I have not written. I have just highlighted it. Like this is the particular branch that should be our solution.
I don't think you have mentioned.
Okay. I mean, the next session I will like rephrase it in a more formal way, then we'll share it.
Okay, sure.
Oh.
Okay then. All right. Bye everyone. Good night.
Okay, good night, thank you.
Thank you.